In this video, we'll talk about using the same ideas we developed for arc length to also talk about surface area. Another way we can use the same ideas from before is to talk about the surface area of solids of revolution. We talked about their volumes a lot previously, and now we also want to talk about their surface areas. So assume we have a function f of x that we're going to revolve around the x-axis, like this picture shows here. How would you find the volume of this shape? Well, the volume of this shape is pretty easily computed by a washer method, right? If I look at washers, that means I'm taking a vertical line like this and revolving around the x. That gives me a washer. In this case, a disk because it's the surface around the axis. And that's pretty easy to work out in this case. You'd probably do this by the washer method. And the integral you would get would be something like the volume is pi the integral from a to b of f of x squared dx, because pi r squared gives me the area of each slice. Adding those up gives me the volume of the entire solid. What if I wanted to find the surface area of this same solid? Well, the idea here is kind of the same. I want to think about the same sort of rotation that would get me washers, but instead do it with arc length instead. And the idea here is, I'm again going to chop this into little pieces and take these little line segments. And what do I get if I rotate each little line segment? Well, now that's more or less parallel to the axis, not perpendicular, so I get a little cylinder there. If I take a little line segment and I rotate that around, I get a cylinder. Cylinders, we also had a method for dealing with solids of revolution, but that was for going the other way and using the shell method. We can sort of use the same ideas here. If I want to find the surface area of this solid of revolution, I need the surface area of each of these shells that I get by rotating little line segments as part of the length of the curve around the axis. And I will need the surface area of these shells to figure out what the surface area of this solid is. How do we find the surface area of the shell? Well, the surface area of a cylinder is 2 pi rh. What's my radius here? Well, the radius is the length this way. It's the function value. And what's the height of the cylinder? Well, the height of the cylinder is actually going to be the length of this segment here. It might seem at first that the height should just be delta x, but it turns out the fact that I have this slope here significantly alters the volume of this cylinder. If it had just been flat at a function value, then sure, it would just be delta x. But because of this slant here in the L term, it's going to significantly alter the volume, and so the better approximation to the height is actually L, not delta x. But we know how to find L. We did this before. This L was square root 1 plus f prime of x squared. That's how we found arc length. So putting all this together, we can get a formula for finding the surface area of solids of revolution. So we assume that our function is bigger than 0, because that gives us something to actually revolve around the x-axis, and that f from existence is continuous. That lets us use the mean value theorem to get that formula for L. Then the surface area, capital S, of the surface obtained by rotating the graph of f around the x-axis between this range of a and b is equal to S is the integral from a to b, again, my bounds like before, 2 pi r, which is f of x, times h, which is root 1 plus f prime of x squared dx. Again, the main way to think about this is 2 pi times r times h for the appropriate cylinder you need to approximate the length of this curve. Let's see an example of what this might look like. So find the surface area of the solid revolution created by revolving the graph of y equals e to the minus x over the interval from 2 to 4 around the x-axis. So for e to the minus x, that's our function. Its derivative is minus e to the minus x. So then we just write out our formula. S should be the integral from 2 to 4 of 2 pi e to the minus x square root of 1 plus e to the minus 2x dx, right? Because I'm squaring, the negative sign goes away, and I get a 2x up top. So to solve this out, this is going to be a little trickier to solve out. I'm going to let u equal e to the minus x. du is minus e to the minus x dx. If I plug this in, I'm going to get a 2 pi integral. I'm going to drop the bounds here and plug them in at the end. Negative sign from the e to the minus x term. Square root of 1 plus u squared du. And now this integral falls in our trig substitution category. Yes, also that stuff comes back. So I want to let u now be tangent of theta. So du is secant squared theta d theta. I get negative 2 pi integral of, this becomes secant cubed of theta d theta, because the 1 plus tan squared becomes a secant squared, square root of secant times the du. And this needs reduction formulas to get to the answer. So using those, I get the following. And then I need to convert this back to u and then back to x. So since tan theta is u over 1, that's my triangle. And so this expression is negative pi times secant, which is 1 over cosine, is just root 1 plus u squared. U times root 1 plus u squared plus log of root 1 plus u squared plus u. Then we convert back to x's because u is e to the minus x. And then I want to plug in 2 and 4 to get the actual surface area. These problems can get kind of nasty, and that's sort of the issue with the fact that there's a square root in the integrand, means these things can get out of control and need things like trig sub and repeat integrals and that sort of thing to get to the actual answer. But the idea of setting up these problems is the important part here. How do you set up an integral to evaluate the surface area of a solid revolution? And that's the formula we discussed before, 2 pi f of x times root 1 plus f prime squared. And that's the important thing here, is knowing how to set up these formulas for the surface area of a solid revolution, given that they're a function revolved around the x-axis.